Hello everyone and welcome to a video about the quotient and product rules for taking derivatives. And I know what some of you may be thinking, well we already covered the power rule. And the reason I put the power rule actually before this is simply because it just makes it easier to check yourself and to make sure that you got this kind of a thing right. However, the power rule will not always it will not always be able to help you here because there are some things where the quotient and the product rules are just needed to actually do the problem correctly. And at a certain point, it'll become almost second nature, and you'll sort of recognize what product rules are what and what quotient rules come out to what, and it'll get easier over time, and we'll get there together. But here we have, let's say we have two functions. We have an f of x and a g of x. Let's say that we have those two things, right? We've got a g of x and an f of x right here. So we've got this here and this here. We need to recognize something before we actually do this, because it is not necessarily that we will be given like a y1 equals something and then a y2 equals something. That's not quite what this is saying. What this is saying is that if you are given, let's say if you're given, scroll over here, let's look at this. If we were given the function of y, and we'll actually solve this out here in a little bit, y equals x squared sine of x, right? X squared sine of x. We can tell that this is just one function. Like if we had to look at this and we were like, if we had to assign it an f of x or a g of x, you would just say, well, hey, that's f of x. Well, why do we even need this? Why do we even need this g of x over here? Well, the reason that we have this g of x is simply because that this is our f of x and our g of x. The y is here is just a function marker, and whenever we have two things multiplied together, we mark that we make a mental note that this function will be rewritten as capital F of x, and then that this becomes our f of x, and that becomes our g of x. So we can isolate these two terms. And so I'll actually do this in two separate colors. So this is going to be green, and this is going to be that sort of yellow. So we have here that f of x equals, and then we have our green, x squared, where that is our f of x, right? We have that is our f of x, and then that our sine x is our g of x. So we could see that these two things are not necessarily just an f of x right here. These two things are actually our f of x and our g of x, and that this marker right here is going to be capital F of x. That way we don't get these two things mixed up. If once we go back over here, we have our equations that we're going to use. And I'm going to zoom out a little bit because they're kind of long and they're kind of crazy looking. But we're going to go through them both together, and we're going to figure the kind of deduce everything that we need. And let's see here, what color should we use? Let's go with orange. I like orange. So we have that the dx, which basically is a general form of the derivative in respect to x of whatever is inside our bracket, is going to be equal, these two right here, these two pieces, is going to be equal to, and remember if we equate that, we have our x squared and our sine of x, those two things being multiplied together is going to be what our f of x and our g of x are, equals f of x, so the original f of x function times the derivative of the g of x function, so the derivative of our sine x, right? Plus our original function, so our original sine x times dx of our x squared. So we can see that, right? We understand, like I said over here, that our g of x and our f of x are not the marker right there. They are actually what is itself inside of the function. And we can, and I think we've broken it up here very nicely, and we'll actually solve this out here in a minute once we get through with this explanation of this product rule. Um, that the product rule allows us to sort of use the power rule in knowing our trig identities and everything of what a derivative of sine x and everything is. As I proved in our introduction to derivatives, we know that that's cosine x, but it allows us to kind of use the power rule, which is why I put it before this video, whereas most cases it's actually after or anything after that, to very quickly and easily use the product rule formula to determine what we need to do here. So if we come over here, we're gonna go down over here, we're gonna use an example of the product rule. Okay? Example of the product rule. And if we remember that our original function y equals x squared sine of x, and we know that that is the same thing as capital F of x equals f of x g of x, I'm sorry. And essentially all we have to do is copy paste everything that we put over here. So we could just say that we know x squared d dx of sine x, and then plus sine d dx of that. So we have x squared d dx of sine x plus sine of x d dx of x squared. And let's break this through, and let's do this all very quickly, just sort of together, and figure out what this answer is going to be. So we know that x squared is going to remain constant, so that'll be x squared. We take the derivative of our sine x, and as we proved in the introduction video, we know that that's cosine x. So we already have an x squared cosine x, and that's the first half of our problem completed. Now we add the plus sign in there to signify basically that the first half is done, and now we're ready to solve the second one. And we know that the sine of x is going to be the same, so we just drag that down again because it doesn't have any operator on it, it's just the sine x. And then we take the derivative of what's inside of our bracket here, and that's 2x, so we have sine of x 2x. And we can already see that this is the correct derivative. This is the derivative, but let's clean it up a little bit because I like my numbers to be simple and easy to read. The x squared cosine x is fine, the way it is, plus 2x sine of x. And that is the derivative of x squared sine of x. And it's very easy to get lost here because we can kind of almost imagine mixing up our f of x's or mixing up the formula, and really the formula is just almost something that you have to commit to memory, which can be unfortunate at times, but it's something that's very reliable to have at pretty much every point in your calculus career. And then let's move on to the quotient rule. The quotient rule is of the same breath as the product rule. The reason I say that is because it's practically the same sort of functionality. If you have two things um, inside of your function, we can actually go ahead and do an example here. So we'll go ahead and set it up like we did with the product rule. Let's say we had a function of y equaling x squared plus x minus 2 over x plus x cubed, I'm sorry, x cubed plus 6. We want a good variety, a good amount of variety with our exponents here to make it not super easy, but something that we can see very quickly. Now here, it's very important that this actually has a very helpful analogous. Uh, um, I guess you could say it's a sort of almost a rhyme scheme to help you remember what to do here, because it's very difficult to remember g of x d dx of f of x minus f of x d dx of g of x, and then over the gx squared is not too difficult. You just remember that that's what the denominator, because we need to note here that this is the same thing as capital F of x equals f of x over g of x. So our g of x, basically what's in the denominator, you square it, and that'll be in the denominator of your derivative function. But if we look over here and we say, well, okay, that's that's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. And if we were to think of that in terms of just a high value and a low value, the numerator being high and the denominator being the low, we can put this in here as uh, low d dx, or just d, low d high minus high d dx, or just d to remember, low over low squared. So you just kind of do low d high, high d low. You know, low d high, high d low. It's very easy to commit to your memory, and it just sort of makes not losing yourself in the formula much easier, especially if you're having to bring it up on a test. Low d high, high d low. It never fails. Over the low squared. You cannot forget the low squared. Otherwise, I promise you, your professor or whoever will tell you that your problem is incorrect. Now, if we were to just rewrite this really quickly, f, we're just going to go ahead and resub that. So f prime of x is going to be equal to um, g of x d dx of f of x minus f of x d dx of g of x over g of x squared. Let's do what we did with the product rule. Let's go ahead and sub in our y function. Our function was y equals, let's see here, y equals x squared plus x minus 2 over x cubed plus 6. Yes. And if we just take that and we say, okay, well, let's replug this in. So let's put this in a nice little, in a kind of a minty color. So we have that is equal. So carry that down. F prime of x is equal to. And let's see here. We have g of x is x cubed. Let's go ahead and put that in our brackets. X cubed plus 6 times the derivative of x squared plus x minus 2 minus, and like I said, remember this is fairly long. It's sort of difficult to keep track of, but if you can do it, it's very helpful. Times, in our brackets, we have our x squared plus x minus 2 times the derivative of x cubed plus 6. And then all of that over, well, let's get a nice kind of straighter line here. All of that over x, and we need to put that in parentheses, x cubed plus 6 squared. Yeah, that is a lot. It is a mouthful of things. We have x cubed plus 6 ddx of x squared plus x minus 2 minus x squared plus x minus 2 ddx of x cubed plus 6 over x cubed plus 6 quantity squared. That is a lot of stuff, but let's break it down just like we did again with the product rule and do it piece by piece. We're going to switch up the color again. Let's go with a nice little kind of violety purple. And we're going to say f prime of x, capital F prime of x, I should say, is equal to, let's see, x cubed plus 6, and we're going to use the power rule just to make our lives a little bit easier, times the quantity of x squared plus x minus 2 ddx. So let's say we're going to take the power rule of that. We get x squared, 2x. The derivative of x squared is 2x plus 1, because we just have an x value, because that denominator increases, that exponent increases to 0, which makes our x 1. And then we have that quantity minus x squared plus 2. So let's say x squared plus x minus 2, sorry, not plus 2, times the derivative, which is going to be 3x squared. Just 3x squared, which is good because we don't have any factors that we have to make. We can just add and distribute 3x squared across that, but we have to factor this over our x. Well, we can go ahead and open that. Let's say x cubed plus 6 over, times x cubed plus 6. And then we can factor that out and get our like terms. So we say, all right, f prime of x capital F prime of x. Let's go ahead and do this factor. So we know our FOIL, first, outer, inner, last. So our first terms, we get 2x to the fourth. Inner, we have our 6 and our plus, so let's see, your plus 12x. And I did it a little bit wrong. Let's reel that back and do the outer first. And so we have x cubed. It wouldn't have really made much difference, but I like the order. Plus, again, so we have our 12x here. And then our last terms, which is just 6. And we have that inside of a parentheses, so that way we do not start doing things with this other set before we're done. So let's see here, we got another bracket. Make that a little bit sharper. Another bracket. And we're just gonna distribute our 3x squared across this polynomial. So we have 3x to the fourth plus 3x cubed minus 6x squared. And another bracket, and then let's go ahead and go down here and FOIL again. So we have, again, let's see here, x cubed times an x cubed, that's x to the ninth. That is x to the ninth, if I'm correct here. Oh no, I am not correct. I apologize. It's x to the sixth. X to the sixth. And then we do our outer terms plus 6x cubed. And then our inner terms plus another 6x cubed. And then our outer terms, which is plus 36. Okay, now we can bring this down again one more time. And I know you're thinking, oh my gosh, this is so long. And it is long, but it's important. And we can see that we're going to go ahead and combine our like terms. So all these are negatives except for this one. This becomes a positive. So let's see here. What are our like terms? So we have 2x to the fourth minus 3x to the fourth. All right, well, that's negative x to the fourth. And then our x cubed minus 3x cubed, so minus 2x cubed, plus 12x minus 6x squared. Well, we can just keep that 6x squared so that's plus 6x squared. And then our plus 12x will also stay. And then plus 6. Plus 6, and then all of that over. Let's see here, over x to the sixth plus 6x cubed. Well, we can actually go ahead and combine those terms in our denominator. So that becomes 12x cubed plus 12x cubed, and then plus 36. Okay. Well, let's factor out our thing since actually what you'll see here, or what you'll find, is that this is unfortunately, this is our derivative. If we honestly, we could have stopped it pretty much right here. Once we combined our top like terms, and then brought down our our brought down. So once we got to this, we didn't even have to factor that, but once we got to this, and we just really went the extra mile here. But this is our derivative. Our derivative is very unfortunately, because it's very large, very, 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 very painful to look at. Negative x to the fourth minus 2x cubed plus 6x squared plus 12x plus 6 over the quantity of x squared plus 12x cubed plus 36. Wow. But that is correct. So, essentially what we found here is that we can look back and say, all right, well, we know how to effectively use, now at least, we know how to effectively use the product rule and the quotient rule, and we are able to differentiate the fact that these f of x's and g of x's are not necessarily actually function markers as much as they are parts of a function that already exists. So, like we said here with our x squared times sine x, the f of x would represent the x squared, and the g of x would represent the sine x. Same thing goes for the quotient rule. And remember the good old rule: low d high, high d low over low squared. Alright, that concludes this video. Thank you for watching.